predict the geometry, not the velocity. Diffusion models that estimate monocular depth and dense 3D point maps usually run inside a compressed latent space, bottlenecked by a lossy autoencoder that blurs sharp object boundaries. PointDiT from Google, ETH Zurich, and Tubingen throws that tokenizer away. A plain vision transformer predicts dense 3D point maps straight from raw image patches, conditioned on frozen DINOv3 features, trained from scratch with flow matching that predicts the clean point map instead of the velocity. The result, the best depth accuracy and the sharpest boundaries at 16 times lower latency than the latent diffusion state of the art. The forward pass. Start from an input image. Encode it with a frozen DINOv3 backbone, taking features from 4 evenly spaced intermediate layers. Sample Gaussian noise on a per-patch grid. Concatenate the noise tokens with the image tokens and run a stack of transformer blocks. The twist, predict the clean 3D point map directly, not the velocity. Recover the velocity by rearranging the flow equation. V hat equals x hat minus z over 1 minus t, clipping the denominator near 1 for stability. Take one Euler step. A single step is already competitive. Predict the geometry, not the velocity. The gap it fills. Latent diffusion for geometry first encodes the scene into a compressed bottleneck, then decodes it back. That round trip caps the boundary sharpness you can ever recover. PointDiT operates in pixel space. On the full point map, no encoder bottleneck, no decoder blur. Frozen DINOv3 carries the image signal across 4 layers, so the transformer only has to learn the geometry. A plain architecture, no hybrid conv head, no intricate geometric consistency losses. The falsifiable hinge on table 3. The central design choice is predicting clean data, called X prediction, instead of the velocity, called V prediction. Switch to V prediction and the model collapses. Boundary F1 falls from 13.5 down to 0.46, depth accuracy from 95 down to 58%, a 29 times collapse on a single design lever. Pixel space diffusion for geometry only works because X prediction works. How scale and steps refine the boundaries. On table 1, boundary F1 against the sampling step count, 3 model sizes. PointDiT base climbs from 8.2 at 1 step to 9.2 at 4, large goes 9.6 to 10.5. Heavy goes 9.8 to 10.5. One step already beats every prior method's best, and each added step sharpens the edges further. The best baseline, Depth Pro, sits at 9.4. PointDiT passes it in a single forward pass. Here is the payoff in pictures. Before, an ordinary photograph, flat, two-dimensional, no sense of how far away anything is. After, a dense 3D point map, every pixel lifted into camera frame coordinates, the geometry of the scene recovered. Edges snap sharp because there is no latent bottleneck. The transformer reads the image and predicts the shape. One step is almost all you need on table 2. At a single Euler step, PointDiT-Heavy reaches a boundary F1 of 9.8, 93% of the 4-step quality of 10.5. Feed all zeros instead of random noise, and it matches. The model has learned a deterministic image to geometry map, not a sampling trick. 16 times faster than the latent diffusion baseline, 72 milliseconds against 178. 5 honest caveats. First, the outdoor inferiority claim is point map error only. On depth, PointDiT-Heavy is actually best on DIOD and E3D, losing only kitty depth. Second, the PPD baseline predicts depth only. Its point map numbers are recovered indirectly, so that comparison is not apples to apples. Third, the headline 10.5 boundary F1 is the large model at 4 steps, narrowly over Heavy at 10.49. No single variant sweeps all 5 metrics. Fourth, the main tables are single seed with no confidence intervals. Fifth, training is synthetic only, 11 million images, bridged to real evaluation purely through frozen DINOv3. Cite the design lever, not a universal depth winner. Predict the geometry, not the velocity. PointDiT is a plain vision transformer that predicts dense 3D point maps in pixel space, conditioned on frozen DINOv3, with flow matching trained on the clean target. Best depth accuracy, sharpest boundaries, 16 times lower latency, and a 29 times collapse if you switch to velocity prediction. Subscribe for the next breakdown.